Welcome to the lecture on forced vibration of a system having rotating unbalance. So we have already studied the vibration, the forced vibration of a single degree of freedom system that is subjected to harmonic uh, force having amplitude f0 and frequency omega. And we have already discussed the frequency response curves and phase angle curves. Now we will take a case of rotating unbalance. Usually the rotating machineries that rotates about certain axis like turbines or motors or some shaft. So they have some unbalanced mass. It could be due to some uh, uh, problem or some weakness in design or due to some manufacturing error. So when there is some unbalanced mass, this unbalanced mass, when the system will rotate about certain axis, will apply certain force, and due to that force, in addition to the rotation, the machinery will also have some vibration in the transverse direction. So therefore we will study today the forced vibration of a system that has some rotating unbalance. So let's show a system and then write the equations of motion and then the solutions, and then we discuss the response, and then we will carry out some numerical examples. So here you can see a system. So here is the element that is rotating, and this is the complete system. That, so it can be a machine that is resting on some elastic pad, so that has some stiffness and damping. Now this machine is rotating, so this is rotating with certain frequency omega, so this is rotating with omega, and here is the unbalanced mass m0. Here m is the total mass. Total mass means that it includes, so it total mass of the system including the unbalanced mass m0, and m0 is the unbalanced mass. So this is the axis of rotation about which our machine is rotating, and from this axis of rotation there is this distance E, the center of gravity of this unbalanced mass. So E is it is we call it eccentricity also. So, it is the distance between the axis of rotation, distance of the CG or center of gravity of unbalanced mass, unbalanced mass from the axis of rotation, from the axis of rotation. Okay, so let us see, I mean this system is rotating and there is a situation, this is the reference axis. From here we assume that the system is vibrating in x direction, and at particular instant of time, here this is omega t, because we measure time from here, and this is omega t, and my mass is at this position. Of course, when it will, with time it will rotate, it will go here, here and so on. Now we have to write the equations of motion. So here we have mass m minus m0, that is balanced mass. So balanced mass is the total mass minus unbalanced mass, and this mass center is here. So we can directly write the equations of motion. So that is d square x by dt square. Okay, so mx double dot. Now for the unbalanced mass m0, we have this distance x plus e, and this is omega t. So this is sin omega t. So m0 d square by dt square x plus e sin omega t. X plus e sin omega t, and this is equal to, so these are the forces on the system due to spring and damper. So they are minus c x dot minus k x. Okay. So now we can see here, we can write m d square x by dt square minus m0 d square x by dt square plus m0 d square x by dt square plus m0 e and d square by dt square into sin omega t. So it is minus omega square if we differentiate twice. So it is cos omega t, then again minus sin omega t equal to minus c x dot minus k x. So these will cancel out. So our equation will be m d square x by dt square plus, so here we can write m d square x by dt square, we can write mx double dot plus cx dot plus kx equal to, so this term we take to the right hand side. So it is m0 e omega square into sin omega t. Okay. So this is the equation of motion of this system. Now we have already performed the derivation of the amplitude response of a system subjected to harmonic force. That is, we have already, if our system is mx double dot plus cx dot plus kx equal to f0 sin omega t. So for this system we have the solution x equal to x sine omega t minus phi, and for which x equal to f0 upon k minus m omega square whole square plus c omega whole square under root. So this already we have derived. Now here if you see here f0, we can put f0 equal to m0 e omega square in this equation, and we can find the amplitude response of this equation number 1. So from this equation we can see that due to this on this unbalanced mass there is some centrifugal force that is proportional to omega square is working, acting on this unbalanced mass. So it is m0 e omega square acting the centrifugal force, and m0 e omega square and its component in the x direction is m0 e omega square sin omega t. So this same force here is represented. Okay. So if we write x equal to m0 e omega square by k minus m omega square whole square plus c omega whole square under root. Now here we can write, we can take k outside from this, so we can write 1 minus m by k omega square whole square plus c omega by k whole square under root, and k will be here, so m0 e by k into omega square. Now we here multiply and divide by m, so we will get m0 e by m into omega square and k by m. So k by m is nothing but natural frequency square, so omega n square upon, and here 1 minus omega square again k by m omega n square whole square plus c omega by k we have already derived, that is 2 zeta omega by omega n square, that is and under root. So from here we can find x equal to m0 e by m into r square upon 1 minus r square whole square plus 2 zeta r whole square under root, or we can write x upon m0 e by m equal to r square upon 1 minus r square whole square plus 2 zeta r whole square under root. So this equation, let us say equation 2, this gives the amplitude of the vibration of the system due to the unbalanced mass. Now the phase angle phi, so here we can write tan phi, that is 2 zeta r upon 1 minus r square. Now again we can plot the curves for x versus the frequency ratio r, and we can see that what are the properties of this kind of vibrations, vibrating system at different frequency and damping. So here we have plotted the, so this is the dimensionless amplitude, because E has the same unit as x and m0 and m has the same unit. So this is dimensionless, and this curve can be plotted here, and we see that when r is very less than 1, it means that omega is much less than omega n. So we have this x by m0 E by m equal to about r square, that is m0, and so here we have the x by m0 E by m very less. So here when we have r very less, it starts from 0. Okay, when omega is 0, so this is 0, because here omega by omega n, omega is 0. So it starts from 0, this response curve, and as soon as we approach to r equal to 1, that is the resonance condition, when omega is equal to omega n, the amplitude is increasing. Moreover, if we increase the damping even at the resonance, the amplitude is lower, and therefore if our operating speed is, we should avoid the operating speed at resonance. However, if we have somehow to pass through the resonance speed, we should increase the damping so that the amplitude is lower. However, when we increase the R, the response amplitude is tending to 1. So x by m0 E by m is tending to 1 as r tend to r is larger. So when r is large, this x by m0 E by m is tending to 1. However, when at resonance, and here if we see the phase angle, so in the next slide we can see the phase angle. So phase angle, when the r is very large, it is tending to 180 degree. So phi is tending to 180 degree. It means that when r is large, the unbalanced and balanced mass vibrate in out of phase. So if m0 minus m minus m0, that is balanced mass, is vibrating in upward, the unbalanced mass will be in the downward. So they are out of phase. At the resonance condition, phi is 90 degree. As we can see, the phase is 90 degree when r equal to 1, irrespective of the value of the damping. And at this situation, the x by m0 E by m, if we put r equal to 1 here, so this is 0 and here it is 2 zeta, and here r equal to 1. So it is 1 by 2 zeta. Okay, so this is the amplitude at resonance. Okay. So now we will take one example, to numerical example, to understand this concept in a better way and to apply on some practical problem. So here we can see the numerical example. It says that there is a figure of turbine, that is Francis turbine, and here is the bearing and there is this shaft, and on this shaft this turbine is installed. So here is this rotor and blades. So from the A side here the water is flowing, it passes through the blades and it gives its energy to the blades. I mean they rotate and so they generate the power. Now we can say so this is the stator, that is static part, and this is rotor, so it is rotating part. You can see the length of the shaft is 2 meter and this is the tail rest. So the water falls down from this in this opening. So it says that the rotor has a mass of 250 kg and an unbalance of 5 kg mm. So it means the rotor, so rotor has a mass. So this is the total mass of the system. So it is m equal to 250 kg and an unbalanced me. So here we took m0 as the unbalanced mass and e the distance from the axis of rotation. So m0 e equal to 5. So m0 into e equal to 5 kg mm. The radial clearance between the rotor and the stator is 5 mm. So there is the 5 mm gap between the rotor and the stator. So one thing we should understand that there is some unbalance in this rotor system. So due to this unbalance the system will vibrate. So if I have this system and here is some unbalance, so this is my rotor and here is some unbalance, let us say, and this is the center, or so it will vibrate in the transverse direction. And due to this vibration it is possible that the rotor may hit the stator and the gap is 5 mm. Okay. So it means that our x is 5 mm. So x is the amplitude of the vibration and the turbine operates in speed range of 600 to 6000. So it is operating in 600 to 6000 rpm range. So it means let us say omega 1 equal to 600 So it is RPM, so we can convert it into radian per second, 2 pi by 60, and omega 2 equal to 6000 into 2 pi by 60. Okay. The steel shaft carrying the rotor can be assumed to be clamped at the bearings. So it is, the shaft is clamped, and so when it is vibrating, we can assume it as a cantilever beam, and I have already derived the how to find the stiffness, how to find the natural frequency of cantilever beam. So we can refer that. So now we have to find the diameter of the shaft, so that the rotor is always clear of the stator at all the operating speed of the turbine. So what is required is the diameter. We have to find the diameter so that the rotor is always clear of the stator, so it doesn't touch the doesn't hit the stator. So it means the maximum x is 5 mm or less. Okay, so maximum x is 5 mm, so it could be less also. So assume damping to be negligible. So here we have to assume zeta equal to 0. Okay, and so let's this is 20 pi and this is 200 pi. So now we have this formula, x by m0 e by m equal to r square 1 minus r square whole square plus 2 zeta r whole square under root. Now zeta equal to 0, so we can reduce this equation, r square upon 1 minus r square. Okay. Now for so what is the we have r equal to omega by omega n, and omega by omega n is root k by m. So here we have two cases of omega. So we have some lower range 620 pi and higher range 200 pi. So we can have, let's say, r1 equal to omega 1 by root k by m. So that is equal to 20 pi upon root k, let's say k is k1 here, k1 k by m. So k by m, so m is 250, and here r2 equal to omega 2 by root k by m, so it is 200 pi by root k by m. Now we put in this equation, so x is 5 mm and m0 e is 5 kg mm upon m is 250 equal to r square. So let's say first we are solving for the r1. So r1 square, so that is 20 pi square by k by 250 upon 1 minus pi square upon k by 250. So from here we can get k, and if we calculate k, so we get 10.04 into 10 power 4. into pi square in MKS unit. Now we take the R2 and here M is 250 and so this is for omega equal to 20 pi, that is omega 1, and here omega 2 equal to 200 pi. So we get k. If we solve this equation for putting R2, we get k equal to 10.04 into 10 power 6 pi square in MKS unit. Okay. So here it is Newton per meter. Now we have two stiffnesses. Which one we should select? We can select only one stiffness. So here the stiffness, because according to the frequency response curve, R should be larger. So R equal to omega by omega n is large. So it means omega n should be smaller, and omega n equal to root k by m. This implies that k is smaller. So k should be small to make omega n small and so the R larger. So we have to select the smaller one. So we select this. So our k equal to 10.04 into 10 power 4 pi square Newton per meter. Now we have to find the diameter, and we know that I said that this is like a cantilever beam. So for a cantilever we have k equal to k equal to p by delta, and delta is p L cube upon 3 ei. So 3 ei by L cube. Okay. And from here we know that I equal to pi d4 by 64 for a circular shaft, and E is the elasticity of the material, and L is the length given here equal to 2 meter. So we know k, we know E, we can take if it is steel it is 200 gigapascal, we can take, we know E, we know L, and I we know pi d4 by 64. So we can replace I equal to pi d4 by 64. From here we can get the diameter. Okay. So we see that how the theory that is based the frequency curve that we already understood helps us to take the decision of the design and to select the correct stiffness, and finally we can get the diameter of the this shaft that is used in this turbine. So we understand today, we study the vibration, forced vibration of a system that has the unbalanced mass, rotating unbalanced mass, and we found out the amplitude and phase, and we understood a problem based on this concept. So thank you for attending the lecture, and see you in the next lecture. Thank you.